In the misty landscapes of early 19th century Scotland, where rolling hills met the endless gray skies, a child was born who would one day decode the hidden rhythm of the universe. James Clerk Maxwell came into the world on June 13, 1831. In a quiet corner of Edinburgh, unaware that his life would one day change the course of science itself. His story does not begin with laboratories or equations, but with curiosity, a boundless, unrelenting curiosity that shaped every breath he took as a child. Even before he could read or write properly, James wanted to know the why behind everything he saw. Why did light shimmer differently on water? Why did soap bubbles show colors that danced and vanished? Why did magnets pull with invisible hands? It was this instinctive desire to understand nature's secrets that separated him from others long before he could define what science truly was. His father, John Clerk Maxwell, was a lawyer turned country gentleman who loved mechanical inventions. His mother, Frances, was intelligent, gentle, and deeply devoted to her son's education. From the earliest days, she guided him with patience and care, teaching him to explore, to question, and to think. They lived on the family estate of Glenlair, surrounded by open fields, streams, and quiet woods. For young James, this was not merely home, it was a living laboratory. Every leaf, every ripple of water, every beam of light was a puzzle waiting to be solved. He carried with him a small notebook, scribbling observations and sketches, trying to trap fleeting patterns on paper. When other children saw the world as a playground, James saw it as an intricate design crafted by invisible laws. But his childhood was not without sorrow. His mother fell gravely ill when he was only 8 years old, and her death left a silence that echoed through the rest of his youth. In her absence, the boy turned even more inward, seeking solace in the beauty of numbers and patterns. Mathematics became his companion, a language that spoke to him when words could not. He began drawing complex geometric shapes with a piece of twine and chalk, tracing ellipses, circles, and ovals on the floor, fascinated by their symmetry and balance. His father, recognizing his talent, encouraged him, though he could not have imagined how far that spark would go. By the age of 10, Maxwell had developed an unusual fascination for geometry. He loved finding patterns in things that others overlooked: the structure of honeycombs, the reflections of light on glass, the curvature of pebbles, the flow of water around stones. Everything for him was connected through shape and motion. He once spent hours studying how colors mixed on spinning tops, noticing how they merged into new hues when the top rotated quickly. This innocent curiosity would later lead him to one of the most important discoveries in the study of color and light. Even in childhood, he was preparing, without knowing it, for the grand symphony of science he would one day compose. When he entered the Edinburgh Academy at 11, James was not the type of boy who stood out by appearance. He was shy, often awkward, and deeply immersed in thought. His classmates sometimes mocked him for his accent and rural manners, calling him dafty, but Maxwell never retaliated. Instead, he immersed himself in study, diving into mathematics, Latin, and natural philosophy. He often filled his notebooks not with simple schoolwork, but with experiments, sketches of mechanical contraptions, reflections on the behavior of light, and diagrams that seemed far beyond his years. His teachers noticed something unusual. This was not mere intelligence, but an almost spiritual connection to logic and order. At school, he encountered for the first time the structured beauty of mathematics, the clarity of geometry, the elegance of algebra, and the power of reasoning captivated him. Numbers and shapes were not abstract to him, they were alive, as if whispering the secrets of the cosmos. He once said that mathematics was the way the human mind could read the thoughts of God. Such was his reverence for the discipline. He saw it not just as a tool, but as a divine language. When most children of his age spent their days in play, Maxwell would spend hours exploring how shapes could be transformed, how one pattern could evolve into another, and how simple rules could explain complex beauty. It was as if he already sensed that the universe was written in mathematical code. waiting for him to interpret it. He built small mechanical models using string, wire, and paper, testing how forces moved through them. He was particularly fascinated by how elasticity worked, how things stretched, bent, and returned to their original shape. These early experiments would later evolve into his groundbreaking studies of the elasticity of solids, a subject that would make his name known across scientific circles. But what made Maxwell unique was not just his intellect, it was his sense of wonder. He combined the precision of a mathematician with the imagination of a poet. He saw beauty in every formula, music in every equation. His mind was never satisfied with surface answers. He wanted to understand the underlying harmony that governed all things. The idea that nature's laws could be expressed in mathematical symbols thrilled him beyond measure. To Maxwell, the universe was not random. It was a masterpiece of design, and mathematics was its poetry. When he was 14, he submitted his first scientific paper to the Royal Society of Edinburgh. The subject was simple in appearance, but profound in implication. It described how to draw mathematical curves with a piece of thread, a method now known as orvoidal curves. His presentation stunned the audience. Here was a teenager explaining geometric principles with the clarity of a seasoned scholar. The Society's members, impressed by his depth of understanding, advised him to continue his studies seriously. This was the first public recognition of his genius, and it confirmed what his father had always believed, that James was destined for greatness. During his teenage years, Maxwell began reading the works of Isaac Newton, Michael Faraday, and other great thinkers. He became obsessed with how light behaved, how it bent, reflected, and refracted. He wondered whether light itself could be something more than what it seemed. Even before he had the tools to prove it, he began to sense that light might be connected to electric and magnetic forces, a vision that would later transform into his electromagnetic theory. But at this stage his ideas were pure intuition born from observation and imagination. At home his experiments grew more daring. He used lenses, mirrors, and prisms to study the colors of light. He made spinning tops painted with different colors to explore how they blended into white when rotated, an idea that would later help him develop the first color photograph. Each experiment brought him closer to understanding the hidden unity between light and form. To the young Maxwell, light was not merely illumination, it was a mystery, a bridge between the seen and the unseen. Maxwell's mind worked like a symphony, where every note, whether from mathematics, nature, or philosophy, came together in harmony. He did not study for grades or recognition. He studied because the universe fascinated him. Every day was an investigation, every moment a question. He once said, "I never make a discovery. I only find out what has been known for a long time." This humility masked the fact that he was uncovering truths that no one before him had fully seen. Even as a boy, he carried within him the seed of a scientific revolution. When he entered the University of Edinburgh at the age of 16, his world expanded dramatically. Surrounded by great thinkers and access to libraries filled with scientific literature, he immersed himself in deeper studies of mathematics and natural philosophy. His professors quickly realized that Maxwell's grasp of mathematical theory was extraordinary. He could visualize complex problems in three-dimensional space and find elegant solutions through geometry. But unlike many mathematicians who worked purely with numbers, Maxwell always tied his equations to the physical world. He believed that mathematics was not separate from reality. It was the framework that described it. He began exploring how fluids moved, how elasticity worked in materials, and how light propagated through different substances. He filled his notebooks with detailed calculations, but also with sketches, analogies, and poetic reflections. To him, science and art were not opposites. They were reflections of the same creative impulse. He often quoted poetry alongside mathematical proofs, believing that both sought to express truth in their own language. In these formative years, Maxwell's love for mathematics evolved into something deeper. It became a way of life. He saw the world through mathematical eyes. A rainbow was not just a display of colors, it was the dispersion of light through refracting water droplets. A pendulum was not just a swinging object, it was a perfect expression of harmonic motion. He understood that everything in the universe followed laws, and those laws could be written as equations. The more he studied, the more he saw unity, a theme that would define his entire career. His early work on curves, color, and elasticity were stepping stones toward a greater realization that all physical phenomena might be interconnected. This idea, still vague in his youth, became the guiding light of his scientific journey. While others studied isolated problems, Maxwell searched for the underlying principles that tied them all together. He was not content with answers to how, he wanted to know why. Maxwell's curiosity extended beyond mathematics into philosophy and theology. He believed that science and faith were not enemies but partners in understanding creation. To him, the elegance of mathematical law was evidence of divine order. He once wrote in a letter that the aim of science was to know the mind of God by studying his works. This spiritual dimension gave his work a rare depth. His equations were not cold symbols but expressions of wonder. As Maxwell matured, his early passion began to shape a worldview that balanced logic with imagination. The precision of mathematics trained his mind to think clearly, while his sense of wonder kept him humble before the mysteries he studied. This balance allowed him to bridge the gap between intuition and calculation, a gift that would later enable him to unify electricity, magnetism, and light into one coherent theory. The young boy who had drawn shapes with twine in Glenlair had become a man capable of reshaping physics itself. But his journey had only begun. His childhood curiosity, nurtured by the quiet landscapes of Scotland and the early guidance of his parents, had laid the foundation for everything he would achieve. Every discovery that followed, from the equations that bear his name to the technologies that define modern life, can be traced back to that simple yet profound trait, the love of understanding. Maxwell once remarked that the true glory of science is to uncover the simple laws that govern the complex. This belief began in those early years when he saw the world not as chaos, but as an elegant design waiting to be revealed. His early curiosity was not just a stage of childhood, it was the origin of his genius, the wellspring from which all his discoveries would flow. The quiet child from Glenlair had begun to hear the music of the universe, and through mathematics, he would one day teach the world how to listen. As Maxwell stepped into the next phase of his life, his curiosity began to evolve from a simple childlike wonder into a disciplined scientific drive. At the University of Edinburgh, he was no longer the shy boy exploring the shapes of ovals with a piece of twine. He was a young scholar filled with purpose, driven by a relentless desire to find unity in the chaos of natural laws. He spent countless hours in the university's laboratories and libraries, surrounded by volumes of Euclid, Newton, and Fourier. Each page seemed to whisper secrets that only he could hear. He saw in these old mathematical works not just knowledge but inspiration, an unfinished symphony waiting for a new composer. His early fascination with patterns and geometry now merged with analytical thinking, giving rise to a style of reasoning that was both intuitive and profoundly structured. He could visualize problems in ways that few others could. For him, mathematics was not merely a set of symbols on a page, it was a living, breathing force that mirrored the heartbeat of nature itself. At this time, Maxwell began forming his first serious scientific questions. How did the invisible forces of electricity and magnetism operate? Could there be a hidden structure to the very fabric of space that allowed energy to move and interact? These questions would later define his life's work, but their roots lay in the fertile soil of his early fascination with mathematics. Every equation he solved and every geometric relationship he explored was like a doorway into a deeper reality. His professors soon realized that he possessed not only an uncommon intellect, but also a creative imagination that made his work original and unpredictable. Mathematics, in his hands, became not just a tool of analysis but an instrument of discovery. His growing passion for understanding natural phenomena through numbers led him to seek patterns everywhere. He studied fluid dynamics, fascinated by the way water flowed around rocks and how whirlpools formed and vanished. He found in these movements an almost musical rhythm, the same kind of order he saw in the dance of light and the shapes of crystals. To him, mathematics was the universal language through which these rhythms could be written. What others saw as chaos, Maxwell saw as structured elegance. He once described the motion of fluids and gases as the poetry of the unseen, revealing his unique ability to merge the scientific with the poetic. During these years, his relationship with his father deepened. John Clerk Maxwell had always been a quiet supporter of his son's passions, but now he recognized that James's talents had grown beyond anything he could guide. Their conversations often wandered from mechanical design to philosophical musings about nature's laws. His father's encouragement provided Maxwell with both emotional strength and intellectual freedom. The foundation of curiosity that his parents had laid in childhood was now blossoming into full-fledged scientific pursuit. His mind was maturing, but his sense of wonder never diminished. Even as he worked through complex equations, he maintained that almost childlike excitement that had driven him since his earliest days. At the age of 18, Maxwell moved to Cambridge University, where his genius would find its true home. Cambridge was, at that time, the intellectual capital of mathematical science, and here he was surrounded by minds as sharp as his own. The transition, however, was not easy. Cambridge had a rigid system focused on mechanical calculation and examination performance. While Maxwell's approach was imaginative and exploratory, he found the routine exercises dull and uninspired. Yet, within this structure, he discovered new ways to challenge himself. He immersed himself in the mathematical theories of Newton, Laplace, and Green, learning the deepest methods of analysis. It was at Cambridge that he realized mathematics could describe not just the motion of planets, but the behavior of invisible fields of force, a concept that would become central to his later theories. He excelled quickly. By 1854, Maxwell had graduated with top honors in mathematics from Trinity College. His professors praised his precision and creativity, but they could not have foreseen how profoundly his mind would reshape the scientific landscape. During these years, he continued to explore geometric and physical analogies. He developed new mathematical methods to describe the mechanical stresses within solids and fluids. His early papers demonstrated a rare combination of abstract reasoning and physical insight, qualities that only the greatest scientific thinkers possess. His approach was never about solving isolated problems. He always sought patterns that linked different phenomena together. In his notes, one can see how his mind worked, a seamless blend of curiosity, intuition, and disciplined calculation. Maxwell's love for mathematics was not the cold affection of an academic, it was passionate and emotional. He saw equations as living expressions of truth. He would spend nights refining his ideas, finding beauty in the symmetry of his results. He often said that the most satisfying part of science was not the discovery itself, but the moment of realization, when everything suddenly fit together, when chaos resolved into harmony. He experienced mathematics the way a musician experiences music. Every theorem, every proof had rhythm, tone, and melody. His sense of awe deepened when he began applying mathematics to light, color, and motion. It was as if the world had given him an instrument, and he was learning to play the song of creation. As a young lecturer at Marischal College in Aberdeen, he continued this intellectual symphony. He began developing what would later be known as Maxwell's stress theory in electromagnetism. He investigated the elasticity of solid materials, describing mathematically how they deform under stress. But even in these technical subjects, his approach remained guided by curiosity. He was not content with mechanical descriptions. He wanted to understand the underlying unity of forces. In the vibrations of elastic solids, he saw analogies to the vibrations of electromagnetic waves that would later carry light. Every calculation he made seemed to echo a deeper question: what is the true nature of energy? It is fascinating to see how, during this period, his childhood interests in geometry and color continued to influence his thinking. Maxwell returned to his early experiments with spinning color tops, refining them into precise scientific instruments. He wanted to know why certain combinations of colors produced white and why others did not. His analysis of color mixing led to one of the most remarkable achievements of his time: the creation of the world's first color photograph. By mathematically analyzing the way red, green, and blue light combined, he demonstrated that any color could be reproduced from these three primaries. In 1861, he projected an image of a tartan ribbon using 3 slides filtered through red, green, and blue light. When superimposed, they formed a full color image, a visual proof that his theory of color was correct. This moment, when the black and white world of photography burst into color, was not just a technical triumph, it was the culmination of decades of curiosity, patience, and love for mathematics. Maxwell's fascination with color was more than artistic, it was deeply mathematical. He understood that light and color could be described with numbers, that the sensations of vision corresponded to measurable physical quantities. He applied calculus and vector analysis to describe the behavior of light waves, treating them as oscillations in an invisible field. In doing so, he laid the groundwork for the modern understanding of electromagnetic radiation. What had begun as a childhood curiosity, the swirling colors of a spinning top, had matured into one of the cornerstones of modern physics. His colleagues admired him not only for his intellect but also for his humility and kindness. He spoke softly, often smiling as he explained difficult concepts with metaphors drawn from nature. Students recalled how he could transform abstract equations into vivid imagery, describing waves as ripples in a sea of energy, or electric fields as lines of invisible tension stretching through space. This poetic approach did not make him less rigorous, it made his insights clearer. He could make the invisible visible through the language of mathematics. During his years as a professor at King's College London, Maxwell's understanding of electricity and magnetism deepened. He was inspired by Michael Faraday, whose experiments had revealed the existence of magnetic and electric fields. Faraday, though brilliant, had no formal mathematical training, and his ideas were often expressed in sketches and intuitive analogies. Maxwell saw in Faraday's work a hidden mathematical structure waiting to be revealed. He began translating Faraday's concepts into precise equations. Through careful reasoning, he developed a unified description of how electric and magnetic fields interact and propagate through space. This was the birth of the electromagnetic field theory, and here, in this great synthesis, one can still feel the echo of his earliest curiosity. The same mind that had marveled at the patterns of light as a boy was now describing those very patterns in the most elegant mathematical language humanity had ever seen. Maxwell's equations showed that electric and magnetic fields are not static forces, but dynamic entities that can generate one another and move through space as waves. When he calculated the speed of these waves, he discovered that they traveled at the same velocity as light. This was no coincidence. In that instant, he realized that light itself was an electromagnetic wave, that electricity and magnetism were the parents of illumination. The young boy who had asked why light shimmered on water had found the answer in mathematics. This monumental discovery, however, was the product of decades of nurturing curiosity, disciplined reasoning, and unshakable love for the abstract beauty of numbers. Without his early fascination with geometry and his instinct to search for unity, Maxwell might never have reached this point. His entire intellectual life was a continuous thread woven from childhood wonder to mature genius. Each stage prepared him for the next, the questions of the boy leading inevitably to the equations of the man. Even in his final years, when illness began to weaken his body, his mind remained luminous. He continued teaching, experimenting, and reflecting on the order of the universe. Friends who visited him at Glenlair remembered him sitting by the window, writing notes and solving equations, still filled with the same curiosity that had defined his life. He spoke often about the beauty of the natural laws he had discovered, not as personal triumphs but as glimpses into a grand design far greater than himself. He believed that human reason, guided by mathematics, could approach the mind of the Creator. For Maxwell, the universe was a vast mathematical harmony, an orchestra of light and energy whose score he had only begun to read. After his death in 1879, the world slowly came to realize the magnitude of his achievements. His equations became the foundation for modern physics, influencing the work of Einstein, Planck, and countless others. Yet, at the heart of all his contributions lay the same force that had driven him from the beginning: curiosity. It was curiosity that made him question, imagination that made him explore, and mathematics that gave him the means to understand. In retrospect, Maxwell's early life appears almost prophetic. Every childhood experiment, every drawing of geometric shapes, every question about light and color pointed toward the destiny that awaited him. He had shown that curiosity, when united with discipline and imagination, can unlock the deepest secrets of existence. His love for mathematics was never about numbers alone, it was about finding order in the universe and beauty in truth. Today, when scientists write Maxwell's equations on a chalkboard, they are not merely solving problems, they are tracing the journey of a mind that saw the universe as a grand design of harmony and light. Those four equations, elegant and eternal, are the distilled essence of one man's lifelong dialogue with the cosmos. The story of Maxwell's early curiosity reminds us that every discovery begins with a question. That wonder is the seed from which all knowledge grows. And so, the boy who once watched sunlight scatter through glass and wondered why, became the man who revealed that light itself was the song of electricity and magnetism, a cosmic dance written in the language of mathematics. His journey from curiosity to revelation stands as one of the greatest stories in human thought, a testament to the power of imagination disciplined by reason. Through his work, James Clerk Maxwell transformed the invisible into the visible, the unknown into the known. He did not merely study mathematics, he lived it, breathed it, and through it, illuminated the world. In the middle of the 19th century, the world stood at the edge of a silent revolution. Steam engines powered cities, telegraphs carried words across continents, and the air was filled with the hum of a new industrial age. Yet behind this progress, a mystery lingered, invisible, untouchable, but everywhere. Electricity and magnetism had become tools of invention, yet no one truly understood their nature. Were they separate forces, or parts of something greater? It was a question that had haunted scientists for decades, and into this question stepped a quiet Scottish physicist, James Clerk Maxwell, armed not with wires or machines, but with mathematics and imagination. The journey that began in the solitude of his mind would uncover one of the most fundamental truths of the universe, the existence of electromagnetic fields. Maxwell had grown up in the shadow of giants. The work of Michael Faraday, the self-taught experimental genius, had already transformed how scientists viewed electricity and magnetism. Faraday's experiments revealed that when an electric current passed through a wire, it created a magnetic field around it, and when a magnetic field changed, it induced an electric current. But Faraday, though brilliant, could not express his discoveries mathematically. He visualized fields as invisible lines of force filling space, curving and moving, connecting electric charges and magnets in a vast web of energy. Most scientists of his time dismissed this as imaginative speculation, beautiful perhaps but not rigorous. Yet for Maxwell, Faraday's vision was not fantasy, it was truth waiting to be written in the language of mathematics. When Maxwell first studied Faraday's notes, he was fascinated by the concept of a field, an invisible structure that could transmit force without direct contact. It was a radical departure from Newton's mechanical worldview, where forces acted at a distance through empty space. Faraday suggested instead that space itself was not empty but alive with energy. Maxwell sensed that this idea, if properly understood, could change everything. To him, the field was not a metaphor, it was real. And he set out to prove it. He began by imagining that the forces of electricity and magnetism were carried by stresses and tensions in a kind of invisible medium. He called it the electromagnetic ether, not a material substance, but a continuous fabric filling the universe. He believed that when electric or magnetic forces acted, they did so by distorting this ether, just as a stretched rubber sheet transmits tension. His task was to describe this invisible dance of forces mathematically. To do so, he returned to the language that had always guided him, geometry and calculus. In his study at King's College London, surrounded by stacks of papers and mechanical models, Maxwell began constructing mental images of how the electromagnetic field might behave. He drew diagrams showing lines of force swirling around magnets, curving around wires carrying current. He imagined these lines as living entities, elastic, flexible, able to store energy. He then translated these ideas into equations, describing how electric and magnetic forces could influence one another in space. Each equation captured a fragment of reality, and together, they began to form a complete picture. His first great breakthrough came in 1855 with his paper, On Faraday's Lines of Force. In it, he attempted something no one had done before, to build a mathematical model of Faraday's invisible fields. He treated electric and magnetic effects as mechanical stresses within a continuous medium, using the principles of elasticity and motion. Though the mathematics was complex and the language of the paper dense, its implications were revolutionary. Maxwell was proposing that electricity and magnetism were not distinct phenomena at all, but interconnected aspects of the same fundamental entity, the electromagnetic field. But the world was not yet ready to understand him. Many scientists at the time still clung to the old mechanical view of nature, a universe of particles, not fields. They could not see how something invisible could be real. But Maxwell persisted. For him, the truth was not in appearances but in patterns. The elegance of his mathematics told him he was on the right path. He continued refining his equations, exploring how changes in electric and magnetic fields might interact over time. He began to notice something remarkable. Whenever an electric field changed, it produced a magnetic field, and whenever a magnetic field changed, it produced an electric one. The two forces were not just connected, they were self-sustaining. Each gave birth to the other in an endless cycle. In 1861, Maxwell presented a new version of his theory in a paper titled, On Physical Lines of Force. This was the first time he used mechanical analogies to represent electromagnetic behavior. Tiny rotating vortices and idle wheels in an invisible medium. These images were not literal descriptions of reality, but tools to help visualize how fields could store and transmit energy. Through these models, Maxwell derived new mathematical relationships between electricity and magnetism. As he refined his work, a pattern began to emerge that would soon change the world. He realized that the combined system of electric and magnetic forces could propagate through space as waves, oscillations of the electromagnetic field, moving at a finite speed. When he calculated that speed using known constants of electricity and magnetism, he found something astonishing. It matched the speed of light. In that instant, 1,000 years of mystery collapsed into clarity. Light was not a separate phenomenon after all. It was an electromagnetic wave. Electricity and magnetism were the parents of light itself. Maxwell's discovery was more than a scientific insight, it was a revelation. For centuries, philosophers had wondered about the nature of light. Was it a stream of particles, as Newton had believed, or a wave in some mysterious medium, as Huygens had proposed? Maxwell provided the answer. Light, he said, is an electromagnetic disturbance traveling through space. Its waves are oscillations of electric and magnetic fields, dancing together in perfect harmony. It was as if he had opened a window into the invisible architecture of reality. Through his mathematics, He showed that every ray of sunlight, every flicker of a candle, every color in the rainbow was part of a vast electromagnetic symphony that filled the universe. To grasp the magnitude of this discovery, one must imagine what it meant in the 1860s. The idea that space itself could carry energy, that invisible fields could move and vibrate, seemed almost magical. It defied the mechanistic philosophy of the time. Yet Maxwell's equations worked. They predicted phenomena that could be measured, effects that could be observed. Slowly, the scientific community began to recognize that a new foundation for physics had been laid. Maxwell had not just described light, he had unified electricity, magnetism, and optics into one coherent theory. But for Maxwell, the discovery was not the end, it was the beginning of a new way of seeing the universe. He continued to refine his equations, simplifying them into a compact set of 4 statements that captured the entire behavior of the electromagnetic field. These 4 equations, now known simply as Maxwell's equations, form one of the cornerstones of modern physics. They describe how electric charges create electric fields, how magnetic fields arise from moving charges, how the two fields interact, and how they propagate through space as waves. To Maxwell, they were more than equations, they were the music of the cosmos written in mathematical form. He believed that the electromagnetic field was a tangible reality, not just a theoretical construct. Every point in space, he said, possesses energy stored in its electric and magnetic components. Even in the vacuum, energy can flow in waves, carrying information and power across the universe. This concept, invisible but measurable, would later inspire generations of scientists to explore the mysteries of radiation, quantum mechanics, and relativity. Maxwell's field had become the invisible fabric of reality itself. Throughout his work, Maxwell maintained the same humility and wonder that had defined his childhood. He never saw his equations as personal triumphs, but as glimpses into the deeper order of nature. In letters to his friends, he often spoke about the beauty of the unity he had found. He compared the interplay of electric and magnetic forces to the balance of harmony in music, each influencing and sustaining the other, forming a complete and self-consistent whole. To him, science was not a collection of isolated facts, but an exploration of divine symmetry. Despite his achievements, Maxwell's work was not immediately celebrated. Many contemporaries found his ideas too abstract, his mathematics too difficult to follow. Even Faraday, whose intuition had inspired Maxwell, struggled to grasp the equations. It would take years, and the later experiments of Heinrich Hertz, to confirm Maxwell's predictions and prove that electromagnetic waves truly existed. But Maxwell himself never doubted. His belief in the power of mathematical truth sustained him. He knew that the universe spoke in numbers, and he had merely learned to listen. What made Maxwell's discovery so revolutionary was that it changed not only what we knew about light, but how we thought about nature itself. The concept of the electromagnetic field shattered the old view of empty space. Space, Maxwell showed, was not a void but a dynamic medium, filled with energy and structure. Forces did not act instantaneously at a distance, they propagated through fields, obeying precise mathematical laws. This shift in understanding was profound. It paved the way for Einstein's theory of relativity, and for quantum mechanics, and for every modern technology that relies on electromagnetic waves, from radio and television to Wi-Fi and satellite communication. The invisible fields Maxwell described became the foundation of the modern world. As the 1860s turned into the 1870s, Maxwell's health began to decline, but his intellect remained unshaken. He continued to refine his theories, teach, and inspire others. His letters from this period reveal a man deeply at peace with his discoveries. He spoke of the joy of finding unity in diversity, of seeing how nature's forces, once thought separate, were bound together by hidden mathematical threads. He knew that his equations were not just useful tools, but expressions of beauty and truth. They revealed that the universe was not chaotic but ordered, not mechanical but harmonious. Even now, more than a century after his death, Maxwell's discovery of the electromagnetic field stands as one of the great turning points in human understanding. It transformed physics from a study of isolated phenomena into a unified science of energy and motion. It revealed that everything we see, every spark, every flash of lightning, every ray of light, is part of the same vast continuum of electromagnetic activity. It showed that we live not in a static universe, but in a sea of dynamic fields, endlessly moving, interacting, and resonating. The story of this discovery is not just a story of science, it is a story of vision. It is the story of a man who saw what others could not, who looked into the invisible and found order, who replaced speculation with certainty, and who, through mathematics, gave form to the unseen. James Clerk Maxwell did not merely discover the electromagnetic field, he revealed a new way of understanding existence itself. Through his eyes, the empty spaces of the universe became alive with energy, and the light that shines upon us became a message from the heart of physics. A message that the world is woven together by invisible threads of force and motion. And so, from the silent equations written in a Scottish study, a new vision of reality was born, a vision that continues to shape our world and illuminate our understanding of the cosmos. The man who once found beauty in geometry and poetry in numbers had now uncovered the very rhythm of the universe. He had taken the invisible forces of electricity and magnetism and shown that, together, they create the light by which we see all things. When Maxwell finally set his pen down, he could not have imagined that his equations would outlive him, shaping the destiny of civilization itself. Yet in the quiet rooms of laboratories across Europe, his invisible world was waiting to be born into reality. Decades later, long after his death in 1879, scientists began to test the strange predictions buried inside his mathematics. They asked a simple but profound question: if light was an electromagnetic wave, could there be others, unseen, longer or shorter, rippling through space beyond the reach of human eyes? It was a question that electrified a young German physicist named Heinrich Hertz. In 1886, he began building delicate instruments, coils, sparks, and resonators, designed to chase Maxwell's invisible waves through the air. Night after night, Hertz worked in darkness, listening to the faint crackle of sparks leaping between brass spheres. And one evening, he saw it, a tiny secondary spark flickering in a receiver across the room. It was faint, almost ghostly, but it proved what Maxwell had predicted decades earlier. Electromagnetic waves were real. The invisible field Maxwell had described mathematically could now be felt, seen, and measured. That small spark in Hertz's laboratory was the first whisper of the modern world. It carried within it the birth of radio, television, radar, and wireless communication. When Hertz demonstrated that these waves could travel through walls, reflect, and refract just like light, he had unknowingly opened a new era, the age of electromagnetic technology. And though he humbly remarked that his discovery had no practical use, within a few short years, others would turn it into one of the most powerful forces shaping human life. Among those inspired was Guglielmo Marconi, a young Italian inventor who saw in Hertz's spark a vision of limitless communication. Marconi imagined a world connected not by wires but by waves, messages leaping invisibly through the air, uniting continents and oceans. Guided by Maxwell's equations and Hertz's experiments, he built the first radio transmitters and receivers. In 1895, he sent the first wireless signal across a field in Italy. 6 years later, his radio waves crossed the Atlantic Ocean. The world gasped. For the first time in history, human voices traveled through the invisible ether that Maxwell had once dreamed of. It was more than technology, it was the triumph of an idea. The electromagnetic field had become not just a scientific concept, but the nervous system of modern civilization. Every pulse of electricity, every flicker of light, every transmission of sound now flowed through the invisible medium Maxwell had revealed. Humanity had learned to harness the unseen, yet the field's mystery deepened as it was understood. When scientists began to explore shorter wavelengths, they discovered that visible light was only a small fraction of a vast electromagnetic spectrum. Beyond the red of sunset lay infrared waves, carrying warmth; beyond violet, the powerful ultraviolet that could alter living tissue. Farther still were X-rays, penetrating flesh but revealing bone; and radio waves, wrapping the earth like invisible tides. The electromagnetic field was not a narrow band, it was a cosmic continuum, stretching from the longest waves that circled planets to the shortest bursts emitted by stars. As physicists mapped this spectrum, they began to see that the universe itself was a symphony of electromagnetic vibration. The stars shone because of it, atoms bound together through it, even the human brain pulsed with its faint echoes. In this realization, Maxwell's field took on a new grandeur. It was not merely a set of equations, it was the language of existence, the rhythm of the cosmos, written in waves. The 20th century dawned under this revelation. Engineers and scientists transformed Maxwell's abstract theory into the foundation of every modern innovation. Telegraphy evolved into radio, radio gave birth to radar, radar led to television, microwaves, and satellite communication. The field that had once been invisible now surrounded humanity everywhere, humming in the background of daily life. But Maxwell's influence reached even deeper. His concept of the electromagnetic field reshaped physics itself. When Albert Einstein began to question the nature of space and time, it was Maxwell's equations that lit the path forward. They were unique. They predicted that electromagnetic waves always moved at a constant speed, about 300,000 kilometers per second, no matter how the observer moved. This defied the logic of Newtonian mechanics, which said that all motion was relative. Einstein realized that if Maxwell's equations were right, then time and space themselves must bend to preserve that constant speed. Out of that realization came the theory of relativity, one of the greatest revolutions in science. Einstein later wrote that the special theory of relativity owes its origins to Maxwell's equations. In other words, Maxwell's vision of the field had forced humanity to rethink the structure of reality. Space was no longer an empty stage where forces acted, it was a participant, a fabric woven with fields and energy. The electromagnetic field had become the prototype for all physical fields, paving the way for quantum theory, particle physics, and cosmology. In laboratories and classrooms across the world, young physicists began to follow Maxwell's footsteps deeper into the invisible. They asked, if fields can carry energy, can they also carry particles? Can light itself behave as both a wave and a particle? These questions led to the birth of quantum electrodynamics, where the photon, an elementary quantum of the electromagnetic field, became the messenger of light. What Maxwell had described as continuous waves, the next generation would see as packets of energy, dancing in probabilistic harmony. Even so, the essence of Maxwell's discovery remained untouched. Whether seen as continuous fields or quantized photons, the truth was the same. The universe is woven from interactions of electric and magnetic forces. The field that Maxwell discovered had become the bridge between the macroscopic and the microscopic, between classical physics and the quantum world. As decades passed, new technologies continued to blossom from his equations. In the mid-20th century, engineers learned to bend electromagnetic waves into beams of coherent light, lasers, capable of cutting steel or reading the data encoded on disks. The invisible field became the backbone of modern medicine, from MRI scanners that peer into the body to radiation therapies that target disease. In space, satellites used microwave signals to navigate and communicate, while telescopes tuned to radio, infrared, and X-ray frequencies unveiled galaxies and quasars across the cosmic sea. Each discovery, each invention, was another verse in the hymn Maxwell had begun. But the true legacy of Maxwell's field was not only in machines, it was in thought. It taught humanity to believe in the unseen, to accept that reality's deepest structures are invisible to the senses yet accessible to reason. It showed that mathematics is not merely a tool, but a bridge between imagination and existence. The field became a metaphor for connection itself, between forces, between ideas, between people. Today, when a smartphone connects to a satellite, when a surgeon uses a laser, When a radio signal carries a voice across oceans, it is Maxwell's field that makes it possible. Every bit of data, every image, every broadcast is a ripple in that same invisible ocean. We live surrounded by the waves he predicted, an electromagnetic universe in constant motion. And though the world has changed beyond anything he could have imagined, the equations remain unchanged, elegant and complete. Even in the cosmos, Maxwell's vision endures. Astronomers studying distant galaxies detect electromagnetic radiation that has traveled for billions of years, carrying the history of the universe itself. The faint glow of the cosmic microwave background, a remnant of the Big Bang, is the ultimate proof that Maxwell's field fills all of space. It connects every atom, every star, every living being in a single network of energy and information. In a sense, the electromagnetic field is the heartbeat of the universe. And yet, behind the grandeur of this discovery lies something profoundly human. Maxwell himself never sought fame or glory. He spoke softly, laughed easily, and found joy in poetry, philosophy, and faith. He once said, "I have never made any discovery myself. I have only helped others to see what was already there." Perhaps that humility is why his discovery endures so powerfully, because it was born not from ambition, but from wonder. His life was brief, he died at 48, but his influence is eternal. Every time light reflects from a surface, every time a radio signal arcs through the sky, every time the northern lights dance above frozen seas, they trace the shape of Maxwell's dream. The field he revealed is not a relic of history, but a living presence, pulsing through every moment of our existence. In the quiet of deep space, electromagnetic waves still travel, carrying echoes of creation. In the circuitry of our technology, electrons still dance to Maxwell's tune. And in the equations that describe everything from atoms to galaxies, his symbols still whisper of unity and harmony. His work reminds us that behind every visible thing lies a world unseen, and that to truly understand the universe, we must learn to see the invisible. Perhaps that is the deepest meaning of Maxwell's discovery. It tells us that the most powerful forces in existence are not those we can touch or see, but those that move silently through the spaces between. Electricity and magnetism, light and energy, thought and connection, all are bound by invisible fields of influence. To recognize them is to realize that the universe is not made of isolated objects, but of relationships, patterns of force and flow linking everything to everything else. In that sense, Maxwell's field is more than a scientific idea. It is a philosophy of unity. It teaches that separation is illusion, that all motion and matter are part of one great continuum. It invites us to imagine the world, not as a collection of fragments but as a single, radiant whole, a field of infinite depth and beauty. And so, the story of the electromagnetic field ends where it began, with a man in a quiet room, listening to the music of mathematics, tracing invisible lines of force through space. From his imagination flowed equations that changed the way humanity sees reality. From those equations came the age of light, of communication, of understanding. And through it all one truth endures, that the universe is alive with invisible energy, and that to see it is to glimpse the hidden harmony of creation. James Clerk Maxwell gave the world more than a theory, he gave it vision. A vision of unity, of elegance, of connection. His discovery of the electromagnetic field remains one of the most profound triumphs of the human mind, a bridge between the tangible and the unseen, between thought and reality. Every photon that shines, every current that flows, every signal that travels through the air carries within it a trace of his genius. In the end, the world he revealed is the world we inhabit, a universe woven from waves of light and energy, forever moving, forever connected. And as we look up at the stars, bathed in the glow of electromagnetic radiance, we are reminded of his legacy, that even in silence, the universe speaks, and its language is the music of the fields. In the heart of the 19th century, when science stood divided between the tangible and the mysterious, James Clerk Maxwell began to weave together forces that had long seemed unrelated. Electricity was a curiosity, lightning tamed into sparks in the laboratory, powerful yet unpredictable. Magnetism was its silent twin, hidden within stones and metals, guiding compass needles but eluding full understanding. Light, meanwhile, was an ancient enigma. Waves or particles, divine or mechanical, no one could say. Each existed as a separate world of wonder. No one yet imagined that all three might be threads of the same cosmic fabric. No one, except Maxwell. He was not a man of spectacle, but of insight. In quiet rooms filled with chalk dust and the faint hum of experiments, he began to sense a connection that others could not see. The story of his unification is not the tale of a single discovery, but of a mind that saw the invisible patterns binding the universe together. Where others saw fragments, Maxwell saw harmony. At the time, scientists like Michael Faraday had already begun to suspect that invisible lines of force might link electric and magnetic phenomena. Faraday's imagination was alive with vision. He pictured fields as real physical entities stretching through space. Though he lacked the mathematical language to describe them, he was a man of intuition. Maxwell was the translator who turned intuition into law. Taking Faraday's sketches of invisible fields, Maxwell began to transform them into equations, lines of mathematics that could describe how these forces interacted, moved, and evolved. His work started with a question so simple it seemed almost naive: what happens when electricity changes? If an electric current produces a magnetic field, as Arosted and Ampere had shown, then could a changing magnetic field produce electricity in return? Faraday had found that it could. This was electromagnetic induction, the principle behind every generator in the world today. But Maxwell wanted more than an experiment. He wanted the universal logic behind it. He began to imagine the vacuum itself as alive with invisible tension, an ether that could carry these changing forces like the surface of a pond carries ripples. In his equations, he expressed how electric fields give birth to magnetic fields, and how magnetic fields, in turn, give birth to electric ones. Each became both the cause and the consequence of the other, locked in an eternal dance. And from that dance, Maxwell saw something extraordinary emerge, a self-sustaining wave that could travel through empty space. This realization was revolutionary. For the first time, it suggested that light itself might be an electromagnetic phenomenon. To test this idea, Maxwell calculated the theoretical speed of these waves based on known electrical and magnetic constants. What he found stunned him. The number was astonishingly close to the measured speed of light. In that moment, the veil lifted. Light was not an isolated mystery. It was the visible manifestation of the same forces that flowed through a wire or turned a compass needle. Electricity, magnetism, and light were one and the same, united under the laws of electromagnetism. That unity was not just a discovery. It was a revelation that changed the meaning of light forever. What humans had once thought of as divine or mystical was now revealed as a natural consequence of physical law. Light was not sent from celestial realms. It was born from the dynamic interplay of fields in space. Every beam of sunlight streaming through the clouds, every flicker of flame, every twinkling star was a symphony of oscillating electric and magnetic waves, racing together through the void. But Maxwell's unification went beyond beauty. It gave the world its first truly modern field theory, a way to describe forces not as distant influences, but as continuous presences throughout space. Before Maxwell, physicists spoke of action at a distance, believing that objects somehow pulled on each other without any medium. After Maxwell, the universe became filled with fields, entities that existed everywhere, shaping everything, even in apparent emptiness. It was a shift so profound that it reshaped physics at its core. Through his mathematical language, Maxwell painted an invisible picture of reality. The equations he wrote were not mere symbols. They were descriptions of how nature breathes and moves. They spoke of balance, symmetry, and conservation. They whispered that every electric field has a story, every magnetic field a rhythm. His four fundamental equations, each simple yet complete, encapsulated the unity of phenomena that had puzzled humanity for centuries. They declared that the universe was not fragmented, but harmonious. It was not easy for the world to grasp what Maxwell had done. His ideas were abstract, his mathematics dense, and his vision decades ahead of its time. Many of his contemporaries found his theory too complex, too theoretical. Some admired his intellect but doubted the physical reality of his predictions. Yet, as time passed, experiment after experiment began to confirm his ideas. Light behaved exactly as his equations predicted. Electric and magnetic forces, once seen as separate, now obeyed the same elegant principles. The unity he had imagined was real. Maxwell's synthesis gave humanity a new sense of order in the universe. For centuries, scientists had searched for the hidden structure behind nature's diversity. Newton had united the motion of apples and planets with gravity. Now Maxwell had done the same for electricity, magnetism, and light. His work extended the reach of human understanding from the laboratory to the stars. The very starlight that crossed billions of miles of empty space was now explained as electromagnetic radiation, following the same rules that governed a spark in a wire. In this unification lay the seeds of the modern world. Once the link between electricity, magnetism, and light was established, invention flourished. Engineers began to see that if light was an electromagnetic wave, then perhaps other types of waves, radio, microwave, infrared, could also exist, each invisible yet governed by the same laws. The field became a new playground for imagination. Maxwell had given humanity a key to the unseen, and with it, they opened doors to technologies that would reshape civilization. And yet, beyond its practical power, Maxwell's unification carried a profound philosophical message. It showed that nature's complexity could be reduced to simple, elegant principles, that the same patterns repeated across scales, from the flicker of an atom to the blaze of a galaxy. It revealed that the universe is not a collection of separate things, but a network of interrelated forces. In his unification, Maxwell glimpsed a deeper order, an order not imposed from above, but emerging from within the laws of physics themselves. There is something almost poetic in the way Maxwell's equations describe light. They tell us that a changing electric field creates a magnetic field, and that a changing magnetic field, in turn, creates an electric field. Each is born from the other. They are inseparable, partners in perpetual motion. This relationship, so perfectly balanced, so endlessly dynamic, feels almost alive. It is as if the universe breathes through these fields, its heartbeat resonating across the cosmos. Maxwell's insight also changed how we understand space itself. Before him, empty space was just a void, a nothingness between objects. After him, space became a living medium filled with energy, tension, and structure. The concept of vacuum lost its emptiness. Instead, it became the stage upon which electromagnetic fields danced. That transformation of thought was monumental. It prepared the way for Einstein's relativity and quantum mechanics, both of which would later reveal that even space and time are not static backdrops, but dynamic entities shaped by energy and motion. To truly appreciate Maxwell's unification, one must imagine the world before it. Picture the laboratories of the early 1800s, crude batteries, iron filings tracing magnetic lines, sparks crackling across brass spheres. These were the symbols of chaos and curiosity, isolated discoveries that spoke of phenomena without a common language. Then came Maxwell, who saw the invisible bridges connecting them all. He replaced confusion with clarity, fragments with unity, chaos with symmetry. In doing so, he gave physics not just new laws, but a new way of seeing. Light, the most ancient mystery of human experience, became understandable at last. No longer a divine spark, it was revealed as the rhythmic pulse of electromagnetic fields in motion. And with that realization, Maxwell closed one of the greatest gaps in science's history. He showed that the forces of the laboratory and the light of the heavens were bound by the same truth. The candle's glow and the starlight of distant galaxies were not different in kind, only in scale. His unification also carried spiritual undertones. Maxwell himself was a deeply thoughtful man. often reflecting on the harmony between science and creation. For him, uncovering unity in the natural world was not just intellectual achievement, it was a glimpse into something transcendent. He saw beauty in the equations, not because they were clever, but because they revealed order where there had been confusion. His unification of electricity, magnetism, and light was more than physics, it was poetry written in symbols, expressing the deep coherence of the cosmos. Years after Maxwell's death, as physicists began to explore the consequences of his theory, the world began to grasp what he had truly achieved. The discovery of radio waves, the invention of wireless communication, the understanding of X-rays, all stemmed from the unification he had created. Each breakthrough was like a new verse in the song of electromagnetism, expanding the harmony Maxwell had composed. His theory became not just a cornerstone of physics, but a foundation of modern civilization itself. Yet for all its power, the unification of electricity, magnetism, and light remains deeply humbling. It reminds us that the universe hides its greatest secrets in the simplest relationships, that profound beauty often lies beneath apparent complexity, and that the forces shaping stars and galaxies also flow through our machines, our cities, even our hearts. As we look back on Maxwell's achievement, we see not just a moment in scientific history, but a turning point in human understanding. Before him, light and electricity were puzzles. After him, they became expressions of the same universal force. His unification was the dawn of a new era, an age where energy, light, and information would define civilization. The invisible field he revealed continues to carry our voices, power our homes, and illuminate our nights. And in every flicker of that light, in every spark that leaps between circuits, Maxwell's unifying vision still lives, echoing through time as one of the most profound revelations ever conceived by the human mind. In the years that followed, Maxwell's intellectual fire only grew brighter, burning with a clarity that defied the boundaries of his age. By the time he entered his late teens, the boy who once drew geometric figures in the sand had evolved into a scholar whose curiosity could no longer be contained by the rigid walls of classical science. His imagination leapt across disciplines, philosophy, mechanics, optics, and the mysterious force of electricity. Each of these threads wove together into a vision so vast that even Maxwell himself might not have fully realized its scale. Yet, through quiet persistence, relentless experimentation, and an unwavering belief in the unity of nature, he began a journey that would transform the invisible into the understandable. As Maxwell matured, his thoughts increasingly centered on the question of unity. What if the same laws that govern motion and heat also governed electricity and magnetism? This question, seemingly abstract, was the seed of a revolution. At that time, scientists were divided. Some studied mechanics, others electricity, and still others light. But no one dared imagine that these forces were merely different expressions of one underlying phenomenon. Maxwell, however, saw hints of symmetry everywhere. He observed how lines of force drawn by Michael Faraday represented something more than artistic patterns. They were windows into an unseen world of field interactions. The idea of a field fascinated him. It suggested that forces were not transmitted through mysterious action at a distance, but through continuous changes in space itself. This vision would soon become the mathematical heartbeat of his life's work. At King's College London, Maxwell's talent found its natural home. The city hummed with industrial electricity, the glow of innovation mingling with the smoke of factories. Yet, within the quiet walls of his study, Maxwell was creating something far more profound than machines. He was crafting the equations that would forever alter humanity's understanding of energy. His work built upon Faraday's experiments, but extended them into a language that the universe itself seemed to speak mathematics. Faraday had seen magnetic lines of force in his mind. Maxwell gave them life through formula. Each equation was like a brushstroke painting the invisible landscape of the cosmos. He began by exploring how electric and magnetic fields might influence one another. Until then, Scientists treated electricity and magnetism as separate siblings, related but distinct. Maxwell's breakthrough came when he introduced the concept of a displacement current, a bold addition to existing theories. It seemed like a small correction, but it changed everything. Suddenly, his equations predicted something extraordinary. Oscillating electric and magnetic fields could sustain one another, traveling through space as waves. These were not just theoretical ripples. They were electromagnetic waves, the same essence as light itself. Maxwell had discovered that light was an electromagnetic phenomenon. In that moment, the world of electricity and the world of optics merged into one. It is difficult to overstate the magnitude of this insight. Maxwell had, through sheer intellect and vision, unified phenomena that had puzzled humanity for centuries. The flicker of a candle, the shimmer of sunlight, the mysterious force that turned a compass needle, all were bound by the same law. His 4 equations, now known as Maxwell's equations, form one of the greatest achievements in the history of physics. They describe how electric charges create electric fields, how currents generate magnetic fields, and how changes in one field give birth to the other. Together, they are the mathematical DNA of light and energy. But Maxwell's genius was not confined to pure theory. He also possessed a deep respect for the physical and experimental world. His imagination was not a cloud of abstraction. It was rooted in the tangible reality of nature. He would often create mechanical models to visualize invisible forces, using gears, pulleys, and rotating elements to represent the dance between electric and magnetic fields. These models were not mere toys, they were bridges between the seen and unseen, helping him, and later others, grasp the elegance of his discoveries. At the same time, Maxwell was a man of profound humility and moral depth. He did not seek fame or wealth. His joy came from understanding, from seeing the divine order in the universe. Many of his contemporaries described him as gentle, reserved, yet profoundly thoughtful. In his writings, one senses not arrogance but awe, a reverence for the beauty of the laws he uncovered. To him, science was not a conquest but a conversation with nature, one conducted through curiosity and wonder. As the years passed, the implications of Maxwell's theories began to unfold. The realization that light was an electromagnetic wave opened a new realm of exploration. If light was part of this vast spectrum, then surely other forms of electromagnetic radiation must exist. Waves of different frequencies and wavelengths, invisible to the eye but no less real. Decades later, scientists like Heinrich Hertz, Guglielmo Marconi, and others would confirm Maxwell's predictions, leading to the birth of radio, television, radar, and eventually wireless communication. Every signal that travels invisibly through the air today, every photon that carries data across the globe, is a living echo of Maxwell's vision. Yet, at the time of his discoveries, the full impact of his work was not immediately recognized. The scientific community struggled to grasp the depth of his unification. The mathematics was intricate, the implications profound. Some dismissed it as too abstract, too theoretical. But Maxwell was patient. He knew that truth, once discovered, would eventually find its place in the world. In quiet conviction, he continued refining his work, confident that future generations would see what he saw, that the universe was woven together by a single, harmonious tapestry of energy. In his private life, Maxwell found solace in simplicity. Despite his towering intellect, he preferred the tranquility of the countryside, the beauty of nature, and the comfort of family. His estate in Glenlair, Scotland, became both a retreat and a laboratory. There, surrounded by the rolling hills of his homeland, he continued to ponder the mysteries of nature. Even in solitude, his mind remained a restless sea of ideas, waves of thought that mirrored the very electromagnetic waves he had mathematically revealed to the world. When illness struck him later in life, Maxwell faced it with the same calm dignity that defined his entire existence. Though his body weakened, his mind remained luminous. In his final months, he expressed no bitterness, only gratitude for the chance to glimpse the patterns of creation. His death in 1879 came quietly, The same year a young Albert Einstein was born, a symbolic passing of the torch. Decades later, Einstein would reflect on Maxwell's work with profound admiration, declaring that the theories of electromagnetism marked the most profound and the most fruitful change in physics since Newton. Indeed, it was Maxwell's equations that laid the mathematical foundation upon which Einstein would later build his theory of relativity. Thus, the unification Maxwell sought was not merely scientific, it was spiritual, intellectual, and timeless. He showed that the laws governing the universe are not isolated fragments, but interconnected harmonies. Through his vision, humanity learned to see light not as a mystery, but as a messenger, a bridge between energy and matter, between the seen and unseen. His legacy continues to pulse through every beam of light, every transmission, every flicker of electricity that powers our modern world. In the end, James Clerk Maxwell did more than turn electricity into light, he turned understanding into illumination. His equations did not just describe the world, they revealed its unity, its coherence, its deep and elegant design. The journey, that began with a child's fascination for geometric patterns, culminated in a theory that would light the path of modern science for centuries to come. The laboratory in London was silent except for the faint hum of instruments and the ticking of a pendulum clock. Within those walls, James Clerk Maxwell was deep in thought, his mind swimming through equations that few could comprehend. He was no longer merely chasing theories. He was now attempting to touch the very essence of nature's hidden forces. The fourth keynote of his life, the unification of light, electricity, and magnetism, was more than a scientific endeavor. It was an act of revelation, a moment when humanity's understanding of the universe expanded beyond imagination. As the 19th century unfolded, electricity and magnetism were still seen as mysterious and separate phenomena. Scientists knew that electric currents could create magnetic effects and that magnets could influence electric charges, but no one had yet understood why this happened or what deeper connection might lie beneath. Maxwell entered this scene with a mind that refused to accept division. He believed that nature did not operate in fragments, that behind every phenomenon was an elegant unity waiting to be uncovered. Through meticulous study, Maxwell began piecing together the clues left by great experimenters before him, men like Michael Faraday, whose vivid imagination had drawn invisible lines of force, threading through space. Faraday had sensed that these lines carried meaning, but he lacked the mathematical tools to express them. Maxwell, blessed with both imagination and mathematical genius, turned Faraday's intuition into a language of equations. He gave the invisible a voice, a way to be measured, predicted, and understood. In his notebook, Maxwell's equations began to take shape, simple yet profound expressions that captured how electric and magnetic fields interacted. Each symbol carried layers of meaning, the curl of a field, the divergence of a force, the rhythm between electricity and magnetism as they danced through space. And then, in a moment of insight that would change history, he saw that these equations described waves, self-propagating ripples of electric and magnetic energy moving together at a finite speed. When he calculated that speed, he found it to be identical to the speed of light. The realization struck him like a flash of illumination, that as light itself was an electromagnetic wave. This discovery was one of the most extraordinary moments in science. It unified the phenomena of electricity, magnetism, and optics into one elegant framework. What had once been three separate branches of study were now seen as facets of the same universal force. In that instant, Maxwell did not merely explain light, he redefined it. He had shown that every beam of sunlight, every spark of electricity, every flicker of flame was part of a grand cosmic symphony of energy oscillating through the vacuum of space. Maxwell's unification was not only a triumph of intellect but of imagination. He did not witness electromagnetic waves with his eyes, he saw them in his mind through mathematics. It was a victory of vision, proof that human thought could reach beyond the senses and grasp truths that even nature kept hidden. Yet, at the time, Many could not fully grasp his achievement. His equations were complex, abstract, and ahead of their time. It would take decades before Heinrich Hertz, inspired by Maxwell's work, confirmed the existence of electromagnetic waves experimentally, proving beyond doubt that Maxwell had been right. What makes this chapter of Maxwell's life truly remarkable is not only the science but the spirit behind it. His pursuit was driven not by ambition but by wonder. He sought harmony in chaos, simplicity in complexity. To him, the universe was a grand design, every field line, every wave, every charge a note in the music of creation. His belief that light and electricity were one was more than scientific unity. It was philosophical, almost spiritual. It was as if he had decoded part of nature's divine language. Through this unification, Maxwell opened doors that would never again close. His equations became the foundation of modern physics, paving the way for radio, radar, television, and the very communication systems that connect the world today. They guided Einstein's theory of relativity, influenced quantum mechanics, and even underpin the technologies that power our digital age. Every photon that lights a city, every signal that crosses an ocean, every image transmitted through the air carries the imprint of Maxwell's insight. In the quiet of his later years, Maxwell must have known that he had glimpsed something eternal. He had looked into the invisible fabric of reality and found unity where others saw separation. In his equations, he did not merely describe forces, he revealed the pulse of the universe itself. And though his life was cut short, the light he uncovered never dimmed. It radiates still in every beam of energy that touches our world, a testament to the man who turned electricity into light and illuminated the very soul of science. The quiet brilliance of James Clerk Maxwell's later years carried the weight of a man who had already reshaped humanity's understanding of nature, yet still sought to connect his discoveries to the deeper rhythm of existence. The fifth keynote of his life, the birth of electromagnetic theory and its enduring impact, was not just the continuation of a scientific journey, but the culmination of an idea that would ignite the modern world. In the soft glow of his study, surrounded by papers filled with flowing equations and ink stains, Maxwell gazed upon the patterns of the universe with both the eyes of a physicist and the heart of a philosopher. He had already united light, electricity, and magnetism into one grand theory, but now he began to realize what this unification truly meant for humankind. The discovery was not simply a triumph of intellect, it was a revelation of nature's deep order. Maxwell understood that his equations did more than describe invisible fields, they spoke of a hidden unity that bound the cosmos together. Each symbol represented a truth that stretched from the tiniest atom to the farthest star. To him, the universe was not chaos but harmony, a delicate balance of forces vibrating in eternal conversation. In the mid-19th century, the world around Maxwell was changing rapidly. The Industrial Revolution had filled cities with the hum of machines and the crackle of electric experiments. Scientists across Europe were attempting to harness the strange power of electricity, but they treated it as a mysterious and unpredictable force. Maxwell's work offered something that had never existed before, a theory that explained electricity not as a curiosity, but as a fundamental aspect of reality. His equations showed that electromagnetic waves could move through space without the need for any physical medium. It was a revolutionary idea, a universe filled not with static emptiness, but with a living field of energy, dynamic and continuous. When he calculated the velocity of these waves and found it to match the speed of light, it was as if the universe had whispered a secret directly to him. Light was no longer a mystery, it was a form of electromagnetic energy. The warmth of the sun, the glow of a candle, the spark from a wire, all manifestations of one elegant law. The beauty of this realization extended far beyond laboratories and blackboards. It connected every human being to the cosmic forces that had always surrounded them, unseen yet ever present. But Maxwell's genius lay not only in his discoveries but in his vision of what would follow. He understood that if these waves could exist, They could be generated, controlled, and perhaps even used for communication. Though he would not live to see it, the seeds he planted would later blossom into the technologies that defined the modern age: radio, television, wireless networks, and the vast web of signals that now circles the Earth. Each innovation that transmitted information across distance was an echo of Maxwell's insight, a ripple of his imagination carried forward by generations of thinkers. In those reflective years, Maxwell often returned to the countryside of Scotland, to Glenlair, his family estate surrounded by open fields and skies heavy with mist. There, far from the noise of the city, he found peace and perspective. He would walk alone along winding paths, his mind alive with thought. The world he had mathematically revealed, waves of energy moving invisibly through the air, seemed almost visible to him now, shimmering between the grass and clouds. His wife, Catherine, who shared his gentle spirit, became his quiet companion through these final years, supporting his research and caring for him as illness began to take hold. Even as his health declined, Maxwell remained undeterred. He continued to refine his theories, to teach, to write, and to share his vision of unity with the world. His lectures were not filled with arrogance or grand gestures, but with calm enthusiasm and clarity. Students often described him as kind, modest, and deeply thoughtful, a man whose intellect was vast, but whose humility was greater still. He believed that science was not merely about discovery, but about revealing the beauty of creation. In every equation he saw evidence of order, purpose, and divine design. The true impact of Maxwell's fifth keynote, the birth of electromagnetic theory, would only be realized after his death, when Heinrich Hertz experimentally generated and detected electromagnetic waves years later. He confirmed Maxwell's prediction with simple apparatus: sparks leaping between metal spheres, waves reflecting and refracting like light. The scientific world stood in awe. What Maxwell had foreseen through pure reasoning was now alive in the laboratory. It was as if his vision had crossed the veil of time to meet the hands of those who followed him. From that moment, humanity began to harness the invisible spectrum of waves that Maxwell had mathematically described. Radio signals spanned continents, radar detected unseen planes, television carried images across oceans, and satellites began to whisper through the void of space. The modern world, wired, luminous, and connected, is the living continuation of Maxwell's legacy. His theory did not remain confined to books. It became the heartbeat of civilization. Yet behind the mathematics and the machines, the essence of Maxwell's work was spiritual. He believed that the pursuit of truth was an act of faith, a form of worship. To understand the laws of nature was to glimpse the thoughts of the Creator. In his quiet Scottish voice, he once wrote that the harmony of the universe revealed the will of Him who made it. These words captured the depth of his worldview, that science and faith were not enemies, but companions in the search for meaning. When he passed away in 1879, at the age of 48, the world lost a man who had illuminated not only science but the very concept of unity itself. His death was peaceful, his life's work complete, though its consequences had only begun to unfold. Maxwell's electromagnetic theory remains one of the cornerstones of physics, standing beside Newton's laws of motion and Einstein's theory of relativity as a pillar of human understanding. And so, the man who once sketched geometric figures in the Scottish dirt became the architect of light itself. His equations live on, whispering through every photon, every pulse of energy, every transmission that carries a human voice across the world. James Clerk Maxwell's fifth keynote was not just a scientific milestone. It was the moment humanity learned that the universe speaks in waves, and that within those waves lies the story of all creation. The sixth keynote of James Clerk Maxwell's life tells the story of influence, the quiet but unshakable power of his ideas as they transcended generations and reshaped the destiny of science itself. When Maxwell passed away in 1879, the world had not yet realized the magnitude of what he had achieved. His equations rested silently in academic journals, elegant but underappreciated. their full meaning waiting for minds capable of seeing beyond the limits of the 19th century. But the seeds he had sown were alive, and in the decades that followed, they would grow into the foundation of modern physics, transforming how humanity perceived energy, space, and even time. It began with a whisper in the halls of European laboratories, young physicists, restless, imaginative, and searching for something greater, found in Maxwell's equations a map of reality that went far beyond what classical science could explain. Men like Heinrich Hertz, Oliver Heaviside, and later Albert Einstein looked upon Maxwell's work with awe. Hertz, inspired by the promise of invisible waves, began experimenting to prove that electromagnetic radiation truly existed. In a darkened room filled with sparks and coils, he confirmed it. The waves that Maxwell had predicted were real. They reflected, refracted, and moved through the air just like light. For the first time, humanity had touched the unseen. Maxwell's vision had crossed from theory into tangible truth. The scientific community was astonished. The realization that electricity, magnetism, and light were manifestations of one unified force redefined physics itself. Maxwell's equations became a universal language, capable of describing the invisible structure of the cosmos. The impact rippled outward, influencing inventors, engineers, and dreamers. Guglielmo Marconi used their implications to send radio signals across oceans. Nikola Tesla and Thomas Edison harnessed the behavior of electromagnetic fields to electrify the world. The quiet equations that Maxwell had once written by lamplight became the heartbeat of a technological revolution. But the influence of Maxwell's thought did not end with technology. It reached into the philosophical core of science. Before Maxwell, the universe was seen as a collection of mechanical parts, moving according to Newton's timeless laws. After Maxwell, it was revealed to be a dynamic web of energy fields, continuously interacting and evolving. This shift in perception laid the groundwork for the next great transformation, Einstein's theory of relativity. Einstein himself often spoke of Maxwell with deep reverence, calling his work the most profound and the most fruitful change in physics since Newton. Without Maxwell's unification of electricity, magnetism, and light, Einstein's exploration of space and time might never have been possible. As the 20th century unfolded, Maxwell's influence continued to expand. His ideas guided the birth of quantum mechanics, influencing the study of photons and electromagnetic radiation. They became the backbone of electronics, telecommunications, and the digital age. Every time a signal travels from one phone to another, every time a satellite transmits an image back to Earth, every time light is bent or captured in a scientific experiment, Maxwell's presence lingers in the equations that make it possible. He is there, unseen but ever active, in every spark of technology that defines human civilization. Yet beyond his scientific impact, Maxwell's character remained an enduring example of humility and wisdom. Unlike many great figures who sought glory, Maxwell never desired fame. His heart was grounded in curiosity, compassion, and faith. He once said that the aim of science was to know the works of God. And this belief infused his discoveries with a sense of purpose beyond personal achievement. For him, uncovering the laws of nature was not an act of dominance but of understanding, a way to read the poetry of creation written in the language of mathematics. His writings and letters reveal a man who saw no conflict between science and spirituality. He believed that the deeper one looked into the natural world, the closer one came to perceiving the divine order within it. His friends often described him as gentle, patient, and endlessly thoughtful. Even as illness consumed his body, his spirit remained luminous, sustained by his conviction that truth and beauty were reflections of the same eternal principle. In the generations that followed, Maxwell's influence became almost mythic. His equations, etched into the annals of physics, inspired countless discoveries, from the structure of the atom to the spread of the Internet. His name stands alongside Newton and Einstein, forming a trinity of minds that defined the very framework of physical law. But while Newton gave humanity the laws of motion and Einstein revealed the relativity of time, Maxwell gave the world its energy, its light, its communication, its electric pulse. He turned the invisible into the accessible and showed that the universe itself was alive with rhythm and resonance. Today, every beam of light that illuminates a city, every radio wave that carries a message, every photon that travels across galaxies is part of Maxwell's living legacy. His influence stretches from the smallest circuits in our devices to the largest cosmic structures in space. And yet, the man behind it all remains as humble in history as he was in life, a reminder that true greatness often speaks softly, through insight rather than power. James Clerk Maxwell's sixth keynote, then, is not just about influence, it is about immortality through knowledge. His ideas did not fade with time, they multiplied, transcended, and illuminated the path of human progress. His vision continues to echo in laboratories, classrooms, and in the very air that carries our voices across continents. He taught the world that even the most invisible forces can be bound by harmony, and that within every flicker of light lies the eternal truth he once revealed. That energy and understanding are one and the same, forever flowing through the vast and beautiful order of creation. In the final chapter of James Clerk Maxwell's story, the seventh keynote shines like a quiet sunrise, the legacy that transcended time and became the invisible heartbeat of modern civilization. It is not merely the tale of a man who discovered equations, but of a mind that revealed how deeply intertwined humanity is with the unseen forces of the cosmos. The work that began in a small Scottish home, carried forward through years of devotion and imagination, became the very foundation upon which the 20th and 21st centuries were built. Maxwell's ideas outlived him, rippling across generations, shaping every form of technology, and redefining how human beings understand light, energy, and existence itself. When Maxwell first wrote down his equations, he could not have imagined how profoundly they would change the world. To him, they were not inventions but revelations, windows into the structure of reality. Yet, as time passed, these four elegant formulas began to form the blueprint of a new age. Scientists would come to realize that everything, communication, power, medicine, exploration, could be traced back to the electromagnetic principles he uncovered. In every flicker of a bulb, every transmission through space, every image sent from one corner of the world to another, his presence endures. He had not just explained the nature of light, he had illuminated the path for all future discovery. The 20th century became the century of Maxwell's awakening. His theories gave birth to technologies that reshaped the human experience. Radio waves carried voices through the air. Television brought moving images into homes. Satellites began to orbit the Earth, guided by electromagnetic communication. The silent dance of waves that Maxwell once described in ink now carried the heartbeat of humanity. Songs, news, images, and dreams moving invisibly across the planet. Without Maxwell, there would have been no wireless world, no global network connecting billions of minds. Every time someone speaks through a phone, listens to music on the radio, or sends a message through space, they are participating in the living legacy of his discovery. But beyond technology, Maxwell's legacy is philosophical. He taught the world to look beyond the visible and to trust in the unseen. Before him, humanity's understanding of nature was mechanical, based on solid bodies, direct contact, and measurable motion. Maxwell introduced a new vision, a world of fields, energy, and waves, a universe where forces ripple across space even when nothing material connects them. This shift was not just scientific but spiritual in its implications. It suggested that reality was far more intricate and interconnected than anyone had dared to imagine. It reminded humankind that even in the vast emptiness of space there is structure, rhythm, and beauty. His influence reached deep into the minds of the greatest physicists who followed. Albert Einstein often spoke of Maxwell as his intellectual predecessor, saying that his theory of relativity rested on the shoulders of Maxwell's equations. Without the concept of constant light speed that arose from electromagnetic theory, relativity itself might never have existed. Later, the birth of quantum mechanics, the study of photons, the smallest quanta of light, also grew from Maxwell's understanding of electromagnetic waves. In this sense, every major revolution in physics since the 19th century traces its roots back to him. Maxwell was not just a scientist of his time, he was a scientist of all time. Even more remarkable than his intellect was his character. Maxwell lived not for glory but for truth. He was soft-spoken, kind, and deeply contemplative. He saw science as a sacred pursuit, an exploration of the divine order woven into the universe. He believed that uncovering the laws of nature was a way of understanding the mind of the Creator. This quiet faith guided his work, giving it depth and humility. In an era when many scientists sought fame and power, Maxwell sought understanding. To him, every equation was an expression of harmony, a glimpse into the infinite. As the decades passed after his death, his influence grew stronger rather than fading. Universities built laboratories in his honor, engineers designed systems powered by his equations, and physicists quoted his name with reverence. His face appeared in scientific halls, but his true monument was not made of stone. It was the light itself. Every glowing screen, every beam of energy that pierces the darkness, every digital connection between human beings stands as a living tribute to him. Today, Maxwell's legacy is not confined to science. It is felt in every act of progress, every exploration into the unknown, the satellites orbiting far above, the telescopes capturing light from ancient stars, the fiber optic cables carrying the world's information, all speak his language. Even the study of the universe's birth, the cosmic microwave background radiation, is understood through principles derived from his work. The light that first emerged from the dawn of time, traveling across billions of years, carries within it the same electromagnetic nature that Maxwell defined. He revealed the pulse of creation itself. And yet, despite all this, Maxwell's story remains that of a gentle soul, a man whose brilliance was matched only by his humility. He never sought to dominate nature, but to listen to it. He once said that the aim of science was to make the unseen seen, and that is exactly what he achieved. He made humanity aware of the invisible fields that shape reality and gave us the means to use them to better our world. His life reminds us that great discoveries come not from power, but from wonder, from the simple desire to understand. In the end, James Clerk Maxwell's greatest legacy was not his equations or theories, but the light of understanding he brought into the human mind. He bridged the gap between mystery and knowledge, between the physical and the spiritual, between darkness and illumination. His work continues to hum quietly in every circuit, beam, and wave that defines modern life. Long after his passing, the energy he unveiled still flows through the veins of the universe, carrying forward his vision of unity, beauty, and infinite connection. The man who turned electricity into light ultimately turned knowledge into power, and that power still illuminates the world.